All right, so we're just going to work through logistics worked example 2 from your textbook. Now, the last two videos have been pretty heavy going. I think this one's much, much easier. There's probably just going to be a couple of little bits that you want to be careful of. All right, so question, insect population is subject to a birth rate of alpha and a death rate of beta plus gamma times the population per head of population per unit time. Ecologists have modeled the rate of change of this population over time using the following logistic differential equation. So here is our differential equation, and we know that alpha is 0.1, beta is equal to 0.05, and gamma is equal to this small number here. And the population is 200 when t is equal to 0. So, a couple of things. Determine each of the following correct to three significant figures. So you want to know N40 and N60. Those are going to be really, really straightforward. So here's our sort of, it's straight out of the textbook, but we don't need much more than that. If the change in n with respect to time is always this function, an minus bn squared, we know that this is our logistic equation here. And this is one you've got memorized, or at least you should have this memorized. All right, so A is equal to alpha minus beta. So this function just looks a little bit different because instead of having an, we've got alpha minus beta n. But that means that alpha minus beta is A. So alpha minus beta is equal to 0.05. And then we have minus gamma n squared. So the b in our initial function here is actually gamma, and gamma is 2 times 10 to the negative 5. So we sub those into the initial equation. We get 0.05n minus 0.00002 to the n squared, and then we can sub all of that into this thing I've highlighted in green, and we'll get nt equals 5,000 over 2 plus 23 e to the negative 0.05t. So nothing fancy. Basically all we've done is used this as our initial function and subbed our a and b values into this function. We want to know what n is at time 40. So we just need to sub 40 in for t. And if we sub 40 in for time, we'll get 978. And N60, same deal, sub 60 in, and we'll get 1,590. The only thing that's like a little bit different here is the average rate of change across the interval 40-60. But this is something that you've done in like, I want to say year 11 Maths B. The average rate of change will be equal to N60 minus N40, so the population at 60 minus the population at 40 over the time it takes to get between those, which is 60 minus 40. So the average rate of change is 31, or 30.6. Okay, so that takes us to I, and then they want to know the instantaneous rate of change when time is equal to 50. So the instantaneous rate of change comes from our derivative function, but there's a small problem because you can't sub t equals 50 into your derivative function because it's not in terms of t. Now you might be getting scared because we had to do all that fancy stuff to put something in terms of t not so long ago, but there's actually an easier way to do it. So the instantaneous rate of change when t equals 50, we can just sub t equals 50 into this equation here. So you can see here we sub t equals 50 into that equation and we'll get 1,286. So what that says is when time is equal to 50, the population is equal to 1,286. So now we can sub 1,286 in to our derivative function because we want to know the instantaneous rate of change when time is equal to 50, which is also when the population is equal to 1,286. And because our derivative function is in terms of n, and we now know that n is 1,286 when t is 50, we can just sub it in there. and we'll get 31.22, which is about the same as 30.6, which makes sense because the rate of change at 40, the average rate of change between 40 and 60 is about 31, and the instantaneous rate of change between those 2 points, 50, is 31.22, so about the same. Part B, graph the function. Well, that's going to be really straightforward because you already know the function is this here. So just putting that into, really putting that into GeoGebra or your graphics calculator, you'll get something that looks like this. And then use algebra to determine when the population has doubled its initial size. So this is, again, very straightforward. The initial size of the population is 200, and we get that from the question itself. And now we just need to know how long until n is equal to 400. So we let n equal 400 in this equation and muck around with a little bit. It's just a little bit of algebraic manipulation, and there's absolutely nothing interesting about that manipulation. There's some exponentials, there's some natural logs, but there's nothing there. I don't need to talk to you about that step by step. And so at time 15.7 or 15.682, the population has doubled its initial size. That question, I feel like it's a real reprieve from the other stuff. There's nothing complicated in there at all. You just need to be careful about when you're doing the instantaneous rate of change, maybe. When t equals 50, the process will be to sub t equals 50 into an equation, find the population, so then you can put the population directly back into this guy here. There are other ways to do it. You can try to put that function in terms of t, but you've seen how to do that and it's not easy. So be aware of sort of how we did that. Just there, 3 lines of working is a lot better than 20 lines of working. Good to go.